Hello everybody, happy Cinco de Mayo. This is the video for the start of Chapter 5. Chapter 5 develops further our idea of integrals, which we introduced in section 4.9. And this section is called Approximating Area Under Curves. So if we let f of x be a function, then from the entire part of the first semester, we know that f of x is the slope of the tangent line, right? So that's what our derivative represented. We talked a lot about that. Now we have just introduced this idea of an integral. And the new question that should be in your head is, what is the integral of f of x dx? So, like, what does this represent geometrically? Because geometrically, the derivative is the slope of a tangent line. What is the integral geometrically? And the answer is that it's the the area under the curve, where the curve is f of x. So basically that's just the area between f of x and the x-axis. So if we look at this picture I've drawn down here, if this is my curve f of x, this is my x-axis, then this area down here that is what the integral of f of x with respect to x is. So you might be asking why, like how do we know that's true? We're going to do a simplified example using position and velocity. So if, let's see here. Sorry, I'm trying to figure out the best way to introduce this. So if we consider position, which we normally write as s of t, and velocity, which we write as v of t, we know that the derivative of position is velocity. And we've also shown that the integral of velocity gives us position. We did that in the last video. And so let's think of like a practical example where we're driving a car and see if our normal ideas of driving a car and distance follow these rules. So let's say we're driving at a velocity of 50 miles per hour, and we drive for half an hour. Hopefully just using basic conversions, unit conversions, you guys could tell me that in that time we would cover 25 miles. Right, we have 50 miles on the hour, we're going half of an hour, so we get half of that 50 miles, 25 miles. But let's see how that transfers into like a graph of this. So if I draw time and velocity, and I want it to be, here, hold on, 10, 20, 30, 40, 50. I want my velocity to be 50 miles per hour. That's what the graph looks like, and I'm saying I'm going, let's say this is half an hour, and this is 1 hour. Then if I cut off my time at half an hour, supposedly this area under my velocity graph should be my position. Specifically, it should be the position at half an hour. So if we were to actually calculate this area, we know the area of a rectangle is base, which is 0.5, times height, which is 50. Note that the base is in hours and the height is in miles per hour. And when we multiply this out, we get 25 hours times miles per hour. The hours cancel, and we get 25 miles, which is what we said above. We'd be covering 25 miles. And so this area indeed is our position after 0.5 hours. Okay, so that's just like a pretty simple illustration of what's happening. We can see that our units check out. We end up with miles. So that's how integration works on like a visual scale. And we know that integration is an exact area under a curve, but we're going to go ahead and take a step back and look at how we can approximate area under a curve. So I'll write that down. Note, integrals give exact area under a curve. But for now, we're going to focus on approximate areas. Actually, before we even discovered, or like humans discovered, that the integral was the area under the curve, they had already invented the idea of the integral, so it was discovered like the way we're introducing it. They had this idea of an integral, and then they later found that it represented the area under a curve. So that's kind of how we teach it. But we're going to focus on approximate areas because, like, what if you didn't have an integral tool, or what if you couldn't take an exact integral? So let's see here. We're going to draw a big graph. Actually, you know what? I'm going to draw 3 small graphs. Wow, that was atrocious. You'll see why I'm drawing 3 in a little bit. Pretend these are all right angles. Anyway, okay, let's say this is f of x and x, f of x, f of x, and x. Okay, so if I were to draw some graph, we're going to have it look like this. And I'm going to go ahead and copy that so we have it on all of them. Okay, I realize now I could have just copied the first graph entirely, but whatever, it's too late for that. Okay, so I could approximate this area. I don't know if you guys ever did this in elementary school. I know I did, because we were supposed to calculate actual areas, and I kind of like, I don't know, cheated the system by drawing rectangles and then guessing and looking at multiple choice. But let's say I were to divide this up into little subsections. So like this. And I want you guys to assume that these have the same width. So each of these little subsections is the same. So let's say like this is 1, this is 2, 3. They each have length that's the same. Okay, so I could draw in little, Here, I actually want this to be a highlighter. I want you able to see underneath it. Okay, I could draw in little squares. That's going to be challenging to see. Okay. I can draw rectangles that look like this. So see how I'm adjusting my rectangle height so that it touches my graph at one of its corners? But once I choose a corner, I have to keep it the same. Right, so because I chose the right-hand corner here, I have the right-hand corner here, the right-hand corner here, and I would just continue on with that. So my right-hand corner is here. And my right-hand corner is here. Okay, so technically, the area under all of these curves is not exactly the area of all these rectangles added, because we have some little parts, like up here, where it's outside of our curve. But if we were to measure the area of this rectangle, the area of this rectangle, and the area of all the other rectangles and add them up, then that would be pretty close to the area under the curve. Hopefully you guys can agree. I can't actually ask you for feedback. But if we can see, we just have like little errors. Like this is a little bit over, this is a little bit over, this is a little bit under, a little bit under, and a little bit over. So when we add this up, it's not going to be exact, but it's going to be pretty close. And this is actually called a left hand Riemann sum. So Riemann, his name was actually Bernard Riemann, and he was a German dude who lived in the 19th century, who looked into the applications of integrals, and he developed this method of subdividing. Oh, cool. I can change my pointer color. Awesome. Anyway, I did not know that. Subdividing the x-axis and taking little rectangles and adding those up to approximate error when you don't know an actual integral. And so the reason this is called a left-hand Riemann sum is because the left side of the rectangle is the one that we made sure matched our curve, right? These left sides match, whereas the right sides don't always match. Okay, so then there's also something called a right-hand Riemann sum. So if I have those same divisions, like here, 3, then a right-hand Riemann sum is going to look, oops. Oh, sorry, guys, I'm sure that you're confused. This is a right-hand Riemann sum, because these are on the right side, not the left side. My bad. Okay, now we're doing the left-hand Riemann sum. Okay, so if I draw in from the left side, I go up to my line on the left side, and come down. Ooh, apparently I did not draw that straight. That's fine. Again, the left side. Left side. Left side and the left side. Okay, so if I color this in, the areas of these rectangles would be like this. And that is our right hand. Wait, I'm losing it, guys. I don't know my left from my right. Okay, my left hand Riemann sum, right? Because we're intersecting at our left hands. Okay, and as you can see, again, this is a pretty good approximation. We do have a little bit bigger of an error here, so it looks like our right hand Riemann sum would be a better estimation. But it's the same idea. It's approximating. There's a little bit of error. We just have rectangles. And then because I have a third graph, there's obviously another one, and it's called the midpoint Riemann sum. And if we have these same divisions, it's actually where we take the midpoint of each of the divisions, so the middle part, and that's what we use. To intersect our curve with, rather than the right hand or the left hand. So these graphs would look more like this. Oops. So see, I'm crossing there at that midpoint. These ones are a little bit trickier to draw, but hopefully you guys get the point. So I have my little individual sections, and I'm taking the middle of those sections, and I'm using that as my x value to find my f of x value, which is what the height of my rectangle is. Okay, so that's what that approximation would look like. And if we shaded in our areas again, we have, it looks like this. And just by looking, it looks like, oops. This one looks pretty similar to the amount of error that we have on our right-hand side Riemann sum. So, yeah. Okay, anyway, that's the introduction to Riemann sums. So we have our right-hand Riemann sum, our left-hand Riemann sum, and our midpoint Riemann sum. And we're just adding up rectangles. And I want you guys to remember that they're the same width for each rectangle. I honestly, when I'm doing this in the real world, I like to use widths of 1 because it's really easy to calculate the area of a rectangle with width 1 because it's just the height times 1, which is just the height itself. But you can change the width, and I want you guys to notice that a smaller width would actually make for a better approximation. So I will do this by using the left-hand Riemann sum since that was our worst approximation. And then that's when we're done for today, so. Okay, so if I look at this left-hand Riemann sum again, and let me clear out the rectangles I had. Let's say I were to cut each of these guys in half. So I'm increasing the number of rectangles, I'm decreasing the width. Let's see what that would do to our approximation. So this is left hand, so we're going up to the left, back down. Ooh, it thinks that's, let me zoom in to see if this will help. Tiny rectangles are not my iPad's thing. Okay, there's one, up to the left, over, down, rectangle. Ooh, weird. The issue with these is I actually have to do a good job of graphing them because that's how you can tell whether or not it's a good estimation. So I'm sorry this is taking a little bit longer than I would normally like on graphics. Okay. So that's what our new rectangles would look like by decreasing the width, increasing the number of rectangles. And if we were to draw in our areas, it looks something like this. Okay, and if we compare this to our previous graph, if we look up here, we have these big chunks of error. And if we look down here, we have much smaller error. So from this, hopefully you guys can tell that more rectangles, which is the same as smaller widths, means less error, which means it's a better estimation. Okay, I actually have a song about this that I'm going to sing for you guys, and I'm so sorry, but I'm not actually. I really like this song. It goes like this. Riemann sums, counting areas of rectangles whose widths get small, we need to count them all. Hey! So, it's kind of stupid, but it does remind you that a Riemann sum is just the areas of a rectangle, and we try to get their widths really small so that when we add them all together, it's a really good approximation for the area under our curve. So, my calculus teacher taught me that eons ago. We will learn in the next section how to use these to approximate errors and how they relate to integrals. But this is just your guys' first introduction to them. So I think that's all we need to cover for your homework. There is one thing I want you guys to note if we look up here. So if we look at this graph, I'll write these in orange. Okay, when our graphs are increasing, if we notice, our right-hand Riemann sums overestimate our area, right? We have this area over the curve that we're overestimating. And when our functions are decreasing, going down, our area is underestimated by the right-hand Riemann sum. And the opposite is true for left-hand Riemann sums. So if our area, or if our function is increasing and we have a left-hand Riemann sum, then it underestimates it. And if our function is decreasing and we have a left-hand Riemann sum, it overestimates it. You might get asked something like that on your online homework. And then the midpoint one, I believe it both overestimates and underestimates most of the time. So if you look here, we have an underestimation here and an overestimation here. But those patterns are kind of interesting to look at for the left-hand and right-hand ones. And you might be asked about it. Alrighty, see you guys tomorrow.